All right, I want you to find the equation of the line tangent to x cubed plus 3x squared when x equals 1. Then I want you, in your calculator, to graph that function x cubed plus 3x squared, as well as that tangent line, and zoom in a lot. And tell me what you see when you zoom in a lot at 1, 4. Go. I want you to find the equation of the tangent line, find, after that, graph that and the original function, and zoom in around 1, 4. And when you write down the equation, don't distribute things all the way. Just leave it like this, but maybe move the 4 over. So you just have 9 times x minus 1 plus 4. Okay, leave it like this. I like the way that looks. No, the original function. Forget inverses. New lesson. This is kind of a one-off lesson, just like the inverses were kind of like a one-off lesson. Yep. You got 3x squared plus 6x, right? Yep. Plug in 1, because we're looking at 1, 4. You get 9. So you get y minus 4 equals 9 times x minus x1. X minus 1. Right? Okay. So there's my tangent line. Looks like that, right? Let's look at it in our calculators. Y equals x cubed plus 3x squared. And then I'm just going to write 9 times the quantity of x minus 1 plus 4. Just like that. And let's zoom standard. Zoom standard. And there's that x cubed graph. And there's my tangent line, right? So I'm going to go trace and type in 1. It takes me right to 1, 4. And then I'm going to zoom in. And before I zoom in, I'm going to make this bold, just so that I know the difference between the two. Okay? So here's my original, and there's my tangent line. I'm going to zoom in around, graph, trace, 1, enter, zoom in. Now what's nice is once you press zoom in once, you just keep pressing enter, and it goes right back to the spot. Okay? So we're close to 1, 4. Zoom in. Okay, let's just make sure we're right at 1, 4. There's 1, 4. Let's zoom in. So there's my original function. There's my tangent line. Zoom in one more. Trace. Go to 1. Enhance. What do we see? one line, right? You see one line, but there's two lines. There is your function and the tangent line. What we've just noticed is the linearization of a function. If you zoom in enough on a specific point, what's going to happen? Well, all of a sudden, what was a curve becomes a straight line. And a tangent line that just nicks my graph at one point ends up looking like it's on top of this graph at all of those points. Okay? Now, is it on top of it at every single point? No, it's going to be a little bit off of it. But the closer we are to 1, 4, this is 1, 4 right here, they will share the point 1, 4. And the closer we are to this point 1, 4, the closer the values of the tangent line will be to this function. Okay? The further we are away, the further away the values are going to be. You know, eventually you get further away and your function will be up here where your tangent line will be down there. Okay? Now, what are we going to do with this fact that a tangent line is pretty much on top of my function at a location or around a specific location when zoomed in? We're going to use this to be able to approximate function values of this. And that is what we're going to do, tangent line approximations. Since a tangent line essentially mimics a function around a location, we're going to use those tangent lines to approximate values of my function that I can't easily do by hand. Okay? So what do I mean? I mean, hey, what is f of 1.1? Well, by hand, I don't want to take 1.1 in cubits and then multiply that by 3 times 1.1 squared. That's going to be tough to do by hand. It'll take me a long time. But instead of doing that, what I can do is use the line that is going to mimic this function around 1. I can use the tangent line at 1, and I can plug in 1.1 into my tangent line to get an approximation for what this is equal to. Okay? So let's go ahead and do that. We are already in kind of the form that we want to be in. I can use this thing, use this to approximate f of 1.1 by plugging in 1.1 for x. So let's see what we get. 9 times 1.1 minus 1 plus 4. 1.1 minus 1, that's just 0.1. 0.1 times 9 is just 0.9. We know that if we're multiplying by 0.1, we're just going to move the decimal place over once. 9 plus 4 is 4.9. So here, using my tangent line, I get that 1.1 gives me the y value 4.9. Well, let's see what the actual value is. In your calculator, figure out what 1.1 cubed plus 3 times 1.1 squared is. Just go into your home screen and type it in. Yes, exactly. I use 1.1 because it's close to 1. I'm not going to use this tangent line to approximate negative 2.1, right? Because that'd be so far away that would not do a good job mimicking the function. We get 4.961. So my function, which is in black, gave me that 1.1 is 4.961. Well, 4.9, pretty darn close to 4.961. We have a good idea of what the function value, or what the value 1.1 cubed plus 3 times 1.1 squared is going to be. Okay? That's something powerful that tangent lines can be used to do. It can be used to approximate tough values that we can't do by hand. Now, the question was, we used 1.1 because it's close to 1. Exactly. Yes. I could ask you to approximate f of negative 0.9. Which means I'd plug in negative 0.9 and cube it, plus 3 times negative 0.9 and square it. That would actually probably take me longer than if I tried to do 1.1 by hand. Would I use an equation of a tangent line that is centered at 1, 4 to approximate f of negative 0.9? No, everybody should be shaking their heads. No. Why? Because it's not going to help me if I have a tangent line over here to approximate a point over here. Instead, I need to use a point, which you might have to decide, or it will be given to you, that is close to the point that you're trying to approximate. This is negative 0.9. Well, typically we'll just use a whole number that we can easily calculate the value of and the tangent slope of that is very close, as close as we can get to negative 0.9, and that will be the value that I use. So if I ask you to approximate negative 0.9, what easy number do you think you will use to find a tangent equation? Negative 1. Okay, so that's step 1. You're going to say, okay, let's focus our attention at x equals negative 1. You're going to find the tangent equation to that function at negative 1. And then you will use that tangent equation by plugging in negative 0.9 into that tangent line equation to approximate what your function value will be. Not inverses. We're off of inverses. Don't use the inverse derivative formula. Just use the derivative rules that we know and love. Plug in negative 0.9, not negative 1. Get your point, get your slope, write your equation of your tangent line. Maybe move over that y minus y1, move over that y1 to the right side because we're going to approximate a y value.
Could you not do it that way? Could you do it that way?
If I asked you to find the estimate for the inverse of f at that, then you would have to use the inverse derivative formula. But we're not talking about inverses at all. So no, we would not do it that way. We got our slope, we got our point. Write your equation. We got our point, we got our slope, we got our equation. Maybe we want to manipulate our equation a little bit. If we so choose, then we use this tangent line equation, which will mimic this function around -1, well, -0.9 is really close to -1. So this will do a good job of approximating what this value actually is. And I can do that by hand, whereas I can't take -0.9 and cube it easily. So I got y equals -3 times -0.9 plus 1 plus 2. This ends up being -3 times 0.1 plus 2. This is 2 plus -0.3, which is 1.7. Okay? I'm assuming that -0.9 cubed plus 3 times -0.9 squared is going to be close to 1.7. Do the math and see what it actually is in your calculator. Original function, not derivative. Now, it's possible. You got to be able to do this calculation by hand. So that's why we're not going to distribute this, because then it makes things more complicated. Because if I got this -0.9 plus 1, boom, 0.1, easy to do by hand. Okay? Okay. What is the value actually? 1.7, what? 01? Awesome. Super accurate. Okay? Now, we can't really know how accurate we're going to be. We can kind of look at the slopes and where we are on the slopes, and really if we are increasing and we're not curved much, then a tangent line is going to be super accurate, really, really close. So we can't really compare the accuracy of this one to the previous one, but we could compare the accuracy between two ones that are kind of close to each other. So if I am looking at x to the 5th plus 2x, and I look at f of 1.1 and f of 1.01, and I know that f of 1 is 3, I'm going to focus my attention at 1, 3 for this one. I can find approximations to both of these, but really right away you should know, okay, one of the two is definitely going to be more accurate than the other. Right? Which one will be more accurate compared to the other? Perfect. The one that is closest to 1. So this one we will be able to check to see will be our approximation much closer, or at least definitely closer to the actual compared to this one. Because the closer we are to our location, if we go back to our picture, the closer we are to this location, the more accurate our line will be compared to the function values. Okay? So let's go ahead and do that as just practice. Find your equation of your tangent line centered at 1. That's going to be your mimicking function for this around 1. And then use it to approximate 1.1 and 1.01. And then check those approximations compared to the actuals. I get an approximation of 3.7 for my first one, and then 3.07 for my second one. And if we check those values, got 1.1 to the 5th plus 2 times 1.1. You get 3.8, so noticeably off, but still pretty close. But then we look even closer to 1 and super close, accurate to the second decimal place. Okay. Now what's also cool is that we can use this to approximate square roots of values that we don't know by the fact that this, now I'm gonna delete this and just start with this. Because on your homework, you're going to see a question like this. Okay? We're going to approximate the square root of 17. Now, a lot of people, when just asked this question with just this information, they don't know where to start. They're not sure what to do. Well, instead of focusing on the number root 17, let's think about what function deals with square roots. Just the square root function. So we are going to say, okay, well, let's look at root x. That's where we start. Okay? Square root of x, we're going to try to approximate root 17. Well, what is that? That is f of 17. Which means my x value that I'm trying to approximate is not root 17, it's 17. Okay? But I need a tangent line, which means I need to center at a point that I can find. What would be a point that I could use that is easy to work with on the graph of the square root of x? 16 and 4, exactly. So I will use the fact that f of 16 is 4. And I have my point that is going to be the point that is going between my tangent line and my function. Use this point, find the slope of the tangent to this at this point, and then use your equation of your tangent line to approximate root 17 by plugging in 17 for x. Okay, go. The answer you will get will be 33/8 or 4 1/8. See if you can get that. You good? Don't let that negative disappear on you. So this is 1 over 2 times the square root of 16. Yep. Yep. The slope you should get, so we're using 16/4 in my tangent equation. Yep.
Okay.
So not 17 because I don't know what the square root of 17 is. I'm using 16.4 because I do know what the square root of 16 is. Excellent. To the negative 1/2. So this is x to the 1/2. And this would be 1/2, positive 1/2. Rewrite this as x to the 1/2. That way you see 1/2 x to the negative 1/2. Now, I don't know what root 17 is, right? But I do know that 17 minus 16 is 1. So you're not going to use root 17. Your x value is 17. How are we doing? I'll rewrite this as x to the 1/2, not x to the negative first.
Okay.
1/2 x to the, so it'd be positive 1/2 x to the negative 1/2. All right, bring the exponent down, subtract 1. Okay, help each other check our neighbors' answers.
The point that you pick has to be close
Yes,
to
right? Because if I'm,
the more.
if I have a function here and I want to approximate this point, but then I use this tangent line, the further you are from your tangent line, the less it's going to mimic your function.
Yes.
You got to be zoomed in at that one location.
I think there's 33 of that, so when I divided it, there was so.
What did you plug in for x?
7.
Yes. So you got 17/8 plus 2, right?
Yeah.
Well, 2 is 16/8.
Oh, okay. Oh.
Now, I see some people simplifying their equations. I would recommend you not simplify your equation of your tangent line. Okay, now first, let's pay attention if we struggled. The derivative, this is x to the 1/2. The derivative is 1/2 x to the negative 1/2. That's the same as 1 over 2 root x. Right, x to the positive denominator because we have a negative exponent. We then use the point that we know, 16.4. I'll use 16 for x. Some people are using 17. Some people are using other values. So I get that, and I have the point 16.4 giving me my equation y minus 4 is equal to 1/8 x minus 16. And I go ahead and don't distribute this 1/8, but just move the 4 over. Now, it asks you to approximate root 17, sure, but we are using the function square root of x when x is 17. The most common mistake made is people plug in root 17 here, when they should just be plugging in 17. So I get 1/8, 17 minus 16 plus 4. That ends up being 1/8 plus 1/18 plus 4. 1/8. Why did I put that? 1/8 plus 4. 4 is 32/8. We get 33/8. You look at the square root of 17, and before I even look at that answer, I'm going to go a step further. Because I know what this looks like. I know this answer is going to be a little bit above the actual square root of 17. Let's see if I'm right. Square root of 17 is 4.123. 33/8 is 4.125. Boom. I was right. This is a little bit above my actual answer. Now, how did I know that? And that's going to be our next step, is not only approximating the value, but also being able to tell somebody if your approximation is an overestimate or an underestimate. I know this is an overestimate. Why? No. No. It actually deals with concavity of my function. Oh my goodness, second derivatives, right? This is something that's concave down. The square root of x, when x is positive, is negative, which means the square root of x is concave down everywhere. Now, I'm going to use a tangent line at this black point to approximate this red point. When I draw a tangent line that goes through a point of a function that is concave down, well, my tangent line approximations are going to be above my actual, which is in red. This is concave down. If I have a graph that is concave up, and I'm using a point in black to approximate a value in red, well, I know that a tangent line will lay under my curve, so my tangent line approximation will be an under approximation. This piece of graph is concave up. Now, the entire graph does not have to be the same concavity. The concavity is only important between your value and the value you're trying to approximate. These would be your intervals where your graph would need to be concave down or concave up. Okay? Okay, so now we can go a step further. By examining the concavity, we can tell if our approximations are over or under. Let's look at x cubed plus 4. We're going to approximate f of 2.01, knowing f of 2 is 12. Now, before we jump in to the approximation, let's recall how we discovered the concavity of something. Second derivative. The signs of my second derivative will determine the concavity of my original function. So my first derivative, which I will need anyways, is 3x squared. My second derivative is 6x. Now, I don't have to do the entire analysis that I did in Unit 4 when I asked you to find points of inflection and asked you when are things concave down, when are things concave up. Really, I just need to look at between 2 and 2.01. Okay? Really, we should make sure that the function is increasing or decreasing, but we'll just assume that they will be doing the same thing and we won't have a max or a min between these 2 points. We just have to look at the sign of my concavity. I know that f double prime is positive between 2 and 2.1. 0, 1. Right? That's just clear. F double prime is positive to the right of 0 and x is positive. So knowing that, I know that this is concave up on my interval in question. Now, you're going to get your approximation, and then you're going to be able to tell whether it's an under or over. When you know something is concave up, don't memorize if your approximation will be over or under. Just go ahead and draw a piece of graph that is concave up. Draw a tangent line so that you know your approximation will be what? Over or under, the actual. Under. Definitely under. You draw your line tangent to your concave down graph, and your points on your line are under, beneath the actual y values of your function. So I just know my approximation is under. I'm just going to call that right now without even finding the approximation. let's go ahead and find the approximation really quickly, and then you guys can get out of here. Your homework is a worksheet, though. I'll leave it at the back. So f prime is 3x squared. F prime at 2 is what we're going to focus on. That's 12. My equation would be y minus 12 is equal to 12x minus 2. Oh, just for, that's great. You get 12.12 as your approximation. That is definitely under because of the concavity of your graph. Your homework is this worksheet. The answers are online. 12.12, which is an under approximation. We will not be practicing for the next quiz. We will just be going over quick homework problems and then quizzing.